All right, so continuing with our Feb March 18 paper. So question 21, they've given you some irrelevant stuff here. The question is NaOH and 1-bromobutane proceeds by an SN2 mechanism. What is the first step in the mechanism? Now, if you're clear about what SN2 really is, you should be fine. Remember, in SN1, which used to happen in tertiary and also secondary, but anyhow, but tertiary alkyl halides, there initially used to have the bond breaking to form an intermediate. Here, none of that happens. So you can just pretty much cross out B, C, and D, because the initial thing that happens is not bond breaking. In fact, what happens is you have your nucleophile, that is OH, and that attacks. If I quickly draw this, I'll just draw the final the rightmost side of it. So Br is slightly positive. Carbon is Br is slightly negative because of high electronegativity. Carbon is slightly positive, and your OH would go and attack your slightly positive carbon, and which is why it's called a nucleophilic reaction, because again, the first attack is by a nucleophile. In SN1, you have the fission happening initially, and then you have a carbocation. So just be careful about that. Okay, compound X can be converted into compound Y in a single step. What could be the identity of compound X? So, well, one thing's for sure, here you have compounds, in the options you have compounds that are like, cyclical in a way, and now they're breaking up here. So what's for sure is that the bond itself has to be breaking. And another thing what's for sure is, if you remember, what's going to happen is you're going to add hot concentrated KMnO4 here, and you're going to watch the double bond break. Now, if the carbon is bonded to, like, let's say one other carbon, if the double bonded carbon is bonded to one other carbon, only one other carbon, then you get your carboxylic acid. So that's the case of one thing here. If the double bonded carbon is bonded to two other carbons,
get a ketone.
You get a ketone, and which is exactly what you have here. So that's what you're going to be looking for. Now you need a carbon that is bonded to one other carbon, and in fact, I believe that's true for that's true for like all options. So that doesn't give us much. Anyhow,
yeah.
But let's look at it like this. Now let's try to give this some numbers. So let's call the carbon that is bonded to one other carbon. Let's call that carbon 1. Let's call this 2. Let's call this 3, 4, and the carbon that was bonded to to two other carbons, we'll call that 5. I won't give this chain a name because, well, it's just gonna be. These are basically just the chains. The last Dundee is basically what I've drawn on the options. Anyhow, so now you have to look for a methyl group on number 2. So now let's try to count. 1, 2, I guess this fits. 1, 2, no it doesn't. 1, 2, it doesn't. 1, 2, I guess this fits as well. But then go 3, 4, 5. 3, 4. So I guess the reason why you can cross out, wait, 3, 4, 5, 6 in fact. So the reason you can cross out D is because it just has too many carbons. It's just too big of a I don't know, of a gola, you could say. Because here, if you exclude the chains, you have 1, 2, 3, 4, 5 carbons, excluding the chains. Here you have 1, 2, 3, 4, 5, 6 carbons excluding the chains, which is why you can cross out D and C anyways. You can cross out B because this particular methyl group is not on number 2, it is on number 3, which is not what you want. So using some numbers, you can figure out that it is A. 23. Which compound reacts with 2,4-DNPH but does not react with Tollens agents? So for 2,4-DNPH, it clearly has to be a carbonyl. Now, which is basically either a ketone or an aldehyde. Aldehydes do react with your Tollens reagent. So if it's not reacting there, it obviously has to be a ketone. So you're looking for a ketone, which is A. This is an aldehyde. This is an well, C is interesting. So C is both ketone and aldehyde. But what you should know, if there's an aldehyde, it would have reacted with Tollens. So you can cross that out because it did not react with Tollens. And D is D is methyl.
It's an alcohol.
Yeah, it's a methyl alcohol, but that doesn't matter. That wouldn't react with either one. So you can just get rid of that. But A would be there. A has a carboxylic acid group and a ketone group. So that's fine. 24, structural isomerism and stereoisomerism should be considered while answering this question. We don't need your help, sorry. Anyhow, the molecular formula of compound X is this much. Compound X reacts with alkaline aqueous iodine. So the iodoform, wait, is this iodoform? No, but
Yeah, aqueous iodine is iodoform.
okay.
It can react with it.
So it's clearly a methyl something. It doesn't necessarily have to be methyl ketone. It could be methyl whatever. Can be dehydrated to form two alkenes only. So basically, when you go from alcohol to alkene, that is your dehydration. But it can only form two alkenes. So that gives you an idea of how the alcohol would be bonded. Now, let's just look at the options because that will be easiest. Now, you can cross out A because it's not a methyl alcohol, because this OH is attached to this carbon, and this carbon is, well, it's attached to like, I don't know, 1, 2, 3, 4. It's attached to like a butyl chain rather than a methyl chain. Same goes
No.
for B, because B is attached to this particular carbon. This OH is attached to this carbon. So it has an ethyl chain on one side and an ethyl chain on the other side. Now C works. C and D both work with regards to methyl methyl alcohols, because, well, they're attached to these two carbons and they have a methyl chain attached to them on one side, so that's fine. But the other thing we have to look at is how it can be dehydrated to form two alkenes only. Well, if you look at, I understand by two alkenes, I believe they're also including stereoisomerism.
Yeah.
Uh, so if you dehydrate C, that should give you, it would give me, this would be CH3, CH3. H would disappear from this particular C because H2O has to go away. So this would be double bond, and this would be CH3. So this would give you, in fact, I believe this would give you just one type of alkene, because it can't undergo cis trans, because, well, the carbon on my left, the left hand side, this one has the same group attached, so it can't really undergo cis trans. Are we justified in saying that?
Yep, we're justified in that.
So we can cross out C, which, well, kind of obviously gives us our answer of D. But let's explain D anyways. Let's see. Kya scene hai? Yes, Hamza?
No, Aisen, the idea is it can give another alkene if you consider the CH3 in a single chain and you form the double bond with that CH3 instead of the CH over here.
What?
So just consider it to be a single chain with the CH3 connected to one carbon.
Yeah.
So that gives you another alkene.
You're saying so C is our answer, in fact, then.
C could be, because on the first CH3, if you form a C double bond with it, you lose a hydrogen and you get two hydrogens instead of it. And you cannot form cis trans isomerism with that either, right?
All right.
So that just gives you two.
Let me just bring people up to pace by drawing this out. So the one type of alkene that we could get from this, I've already drawn. I rubbed that, but you can rewind the video to see that. But the second type of alkene, the second type that you could get from C, is that if you take the hydrogen from the one on the right, so that would give you CH, and CH3 remains as it is. That gives you CH, the OH goes away, and from this, instead of CH3, one H goes away and you get CH2. So obviously this can't undergo cis trans either, because the one on the right has two hydrogens attached to it, so it's like the same group attached to it. So this can't undergo cis trans either, which means that this clearly would be the one that I just drew would be one of the alkenes, and the other one that I drew before would be the second one. So it could only have two alkenes, which works. The reason why it can't be D, although I don't want to go into too much depth, but if you just look at D, so if I can just do this without while being a little lazy. So if you can take OH from here and H from here, that gives you one, and that doesn't have an isomer, so that is like one alkene you can draw. However, you could also take OH from here and H from here. In this particular case, what you'd get was you'd get CH double bond CH3, and you'd get CH2 CH3. Now this in this cis trans would happen because different bond, different things bonded to the carbons. So cis trans would happen. So this would not be one isomer. This would be two isomers. So you have the one isomer if you took this side. You have the two isomers if you take these two, and hence you would get three for D, not two. And hopefully that's clear why you can stay with C rather than going on with D. Anyhow, even if it isn't clear, it's fine. Just leave the question. 25. Which volume of hydrogen measured under measured under room conditions is produced when 0.160 grams of methanol reacts with excess sodium? So if we look at methanol, so that is CH3OH plus Na gives you CH3ONa plus half H2, because hydrogen is not going to be H, it's going to be H2, right? Which means there's a 1 mole to half mole ratio between methanol and hydrogen gas. We don't care about sodium because, well, sodium is in excess. Now, if you can figure out the moles of methanol, that would give us a good idea. So the moles of methanol are mass upon mr. So the mass was 0.160 upon mr would be 12 plus 16 is what, 28, 29, 30, 31, 32. Oh, did I do the mental math correctly? I'm very bad at mental math. Yeah, I think I did it fine. Anyhow, so this would give you the moles of methanol. You can do it by ratio method if you like, whatever. Hamza, how many moles would we get by 0.16 upon
5 into 10 to the power minus 5 into 10 to the power minus minus 3.
So this is minus 3. Now, if you think about this, so 5 into 10 to the power minus 3 moles, right? In fact, let me do this to the ratio method. So 1 mole gives you 0.5 half moles of H2. So this is methanol and this is H2. 5 into 10 to the power minus 3 should give you what? It should give you 2.5 into 10 to the power minus 3 moles of H2. Basically just divided by half. You can do it via the ratio method. Anyhow, so you have 2.5 into 10 to the power minus 3 moles of H2. You need to figure out which volume, what is the volume, and you can do that using your ratio method as well. So 1 mole gives you 24,000 cm cube. I'm not taking it in dm cube because that's just what the options are in, so I just converted it. And 2.5 into 10 to the power minus 3 gives you x. So x goes over there. X is basically you just multiply these two. So 2.5 into 10 to the power minus 3.
60 centimeter.
60, which is A. And we can proceed.
Yeah.
Okay.
Listen, I'll join you in a few minutes now.
All right, no issues. Anyhow, question 26. Compound X produces a carboxylic acid when heated under reflux with an acid with acidified potassium dichromate. So basically, compound X is being oxidized. Compound X does not react with sodium metal, so you can kind of cross out your alcohols because your alcohols would react with sodium metal to liberate hydrogen. That is like literally what we did in question 25. And it doesn't matter whether they're primary or secondary, alcohols will always react with sodium metal. Okay, so but propanone won't, and the aldehyde propanol won't either because it doesn't have that OH bond. Anyhow, so what could be the identity of compound X? Now, what you should know that an aldehyde can be oxidized to a carboxylic, so this can happen. Sorry, so this can go to a carboxylic acid, that's fine if you oxidize it. But if you have this, well, this will never go to a carboxylic acid no matter how much you oxidize it. The ketone won't. So, which is why you can just stick to 26A. 27, a reaction occurs when a sample of 1-chloropropane is heated under reflux with NaOH dissolved in ethanol. Okay, so NaOH in ethanol is definitely elimination. Normally, sodium hydroxide could have done stuff like substitution, but when you see it in ethanol, but then you should know that again heated under reflux as well. You should know that that is definitely elimination. Those were the conditions for elimination. I don't know how else to explain it. There's something that one should know. Anyhow, so what would be the product? It would not be propanol, it would be propene, because like what happens is, if you think about this, you had this, attach the hydrogens by yourself, whatever. So, or let me just do it anyways. So CH2, CH2, um, CH3. Yes. So what then happens? You get Cl from this particular carbon. From the other carbon adjacent to it, you get a H. So that gives you CH3, CH double bond, CH2, and HCl formed separately. Excuse the bad handwriting. Anyhow, so that gives you, clearly gives you propene, not propan 1 all. So that gives you B. Ethan dioic acid has the formula of well, this. Well, what is the formula of aluminum ethan dioate? So if you kind of remember the idea, well, with sodium, sodium used to come and used to just displace the hydrogen. But in this particular case, what happened with sodium? Sodium was just Na positive, so it was fine with that one negative charge the oxygen would provide, because the oxygen is kind of like this. It goes like this. It's like this. This gets removed. This is negative. This is positive. That's what happens. However, if you have aluminum here, well, aluminum has 3 positive. This needs to be into 3. However, another twist that they've given in this particular question is that there are two such groups here and here. So the idea here is, if you have, like, let's say aluminum on this side and aluminum on this side, what do both of these need? They don't need one, they need 3 of these, because if they have 3 of these, then the right hand side can satisfy this aluminum, and the left hand side can be okay with this particular aluminum. So that answer would be D, I believe, because you have air 2, so your aluminum on your right and your aluminum on your left, and since each aluminum needed 3 times this, you just took whatever was in the middle into 3. C2O4 is basically the ion, so like you take that into 3. Another way to look at this, in case you didn't understand this explanation, that's completely fine. I can explain this through another way. Perhaps that'll be a little simpler way to look at it. Is what is the ion? The ion is this: negative, negative. You can also write the ion in terms of this. That's what this is, the molecular formula, right? But remember, this particular thing has 2 negatives, because well, negative from here, negative from here. So now if you write 2 negative inside, this is multiplied by 3, which gives you 6 negative. And aluminum is 3 positive into 2 is also 6 positive. And this is the only one that makes sense. These all wouldn't balance out. So you can cross them, you can just do over D. So that's another way you can look at it. Alcohols, aldehydes, and nitriles can be converted into carboxylic acids. Which description of their conversions into carboxylic acids are correct? So nitriles hydrolyze. If you remember, you used to add concentrated HCl or dilute HCl, but you used to add acid to nitriles and you heat them and they go to carboxylic acids, and you used to call that acidic hydrolysis. You could also call it oxidation, but well, the preferred term is hydrolysis. That's what they prefer in the marking schemes for paper 2, and that's what they'll use in paper 1 as well. So alcohols obviously would oxidize to carboxylic, and the same thing goes with aldehydes. That should be kind of obvious, because you add oxidizing agents. You add chromate or potassium or KMnO4 to alcohols and aldehydes, and you reflux that gives you carboxylic. So obviously these two will be oxidation. You can cross this out. So the question is whether nitrile is hydrolysis or oxidation. If you remember the correct terminology we use in this particular case, it is acidic hydrolysis, not oxidation. So that's why you can get C rather than B. How many structural isomers with the molecular formula C4H10O give infrared absorptions both at approximately 1200 centimeter and approximately 3400 centimeter? Okay, well, so what are we looking for at 1200 and 3400? Interesting question. Okay, so we were looking for 1200 and 3400. So 3400, it could be, is it amine? What do we have? But it can't be amine because we don't have N. We just have one O, remember, so it can't be a carboxylic either. So 3400 would probably be, it can't be a carboxylic, so some sort of an alcohol, because carboxylic would require two oxygens. We do not have that. And uh, you have another one at around approximately 1200, and the only thing I can look for 1200 is this, which is basically CO, which doesn't really help you much because CO can either be alcohols, ethers, esters. Can't be esters in this case because we only have one oxygen here. Anyhow, so what we're basically looking for, we're looking for well, some sort of, what we can say, we're looking for an alcohol basically, or we're looking for, I don't think it can be ether. Can it be? Because if it's just ether, if it's an alcohol, then it would give a peak in 1200 because that's what it shows. Alcohols do, and it would give a peak in 3400 as well. If it was just an ether, it would not give both peaks. It would just give a peak at 1200. It wouldn't give a peak at 3400. So I don't think it can be an ether. It can be esters or carboxylic either because they need two oxygens. So let's try to figure things out. So basically, what they're trying to say is how many structural isomers that are alcohols can happen for C4H10O. That's the idea. That's literally it. So I think our work with the data booklet is done. Yeah, our work with the data booklet is done. Let's look at how many structural isomers are alcohols for C4H10. So COH, that's one. Let's draw another one. OH, C, 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 that is two. Let's draw another one. OH, C, 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 so that is three. Can we have any other scenario? Well, if you think about it, so this was all, I made chains. Maybe I can now start to look at secondary alcohols. So C, 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 instead of one, I can add it at two. So that will give you four. And you have to be very careful here to ensure that nothing really overlaps. So for example, if I wanted to make something of this sort, well, if I wanted to make something of this sort, if I had a C here, and I want to draw an OH over here, I have to check to ensure that I haven't done something of that already. And in fact, in this case, I believe I have, because if you think of it, if you think of this as this, no, have I? In fact, I have. Obviously, I have. I've already drawn a tertiary alcohol. So I believe I can't think of any more. I was never very good at these questions though. I believe it'll be B. But just do hold on a second. It's already I'm done with 30 questions, so I have to check my answers anyways. So I'll see if I did this question correctly or not. So let me check these 10 MCQs. Okay, so is it still intact? Because for somehow we managed to get these 10 MCQs correct as well. This was B that I was being a little confused in, which is surprising because normally I used to get these questions wrong all the time in AS. Anyhow, so these 10 MCQs were fine. Our answers are marked correctly, and so you just refer to the explanations that we provided. And for the last 10 MCQs, and to conclude this paper, we'll have the last video. We'll see you there.